morning to all of you. In the last lecture, we introduced the concept of an atom as we understand today, and we said that the main task for us would be to understand what the structure of the atom is. One knows that atoms are electrically neutral and atoms also have electrons in them, because that is something that is experimentally seen. Therefore, there must be a background positive charge which neutralizes the charges of the electrons. So, the big question when it comes to the structure of the atom is the manner in which the negative charges, namely the electrons, and the positive charges are distributed. And we also know that the atom is much heavier compared to the electrons, even if you take the masses of all the electrons into account. Even in the simplest case of the hydrogen atom, for example, you can make use of Avogadro law, etc., to estimate the mass of the atom. You see that the atom is 2000 times heavier than the electron. So, what are we saying? We are saying that the mass of the electron is of the order of 0.5 MeV by c squared, whereas the mass of the atom, the mass of the electron is 0.5 MeV by c squared, whereas the mass of the atom is of the order of 1000 MeV by c squared, 1 GeV. So, it is of great importance to know whether this very large mass, thousands of times larger than that of the electron, is distributed uniformly over the volume of the atom, or it is concentrated in some particular region, typically the center of the atom. That is the question. I also told you that there was one model due to Thomson, where Thomson argued that the positive charge is distributed over the entire volume. So, this is the picture that I was showing you. So, please concentrate at the second figure. So, we assume that the background grey, bluish grey color represents the uniform distribution of the positive charge, and the small yellow pebbles or bullets that you see represent the electron. So, this was the conventional wisdom, although there was no experimental evidence. Now, what Rutherford did was to set forth to verify this model. We should remember that Rutherford did not suspect this model, but he wanted to verify this model because it appeared to be completely plausible, probably because people could not think of such a large mass being concentrated at one single point or in a very small region in the space. That is what he tried to do. And of course, in any case, this model is quite different from the earlier primitive model, which was advocated by Kanada or Democritus or Newton or Dalton, all these people, where they imagined atom to be attributeless except that it is a very hard sphere. But we have made a significant improvement when going from this to this. We have the concept of charge, we have the concept of electromagnetic interaction. As I told you, this picture cannot be taken completely literally, because if you have a positive distribution of charge of this particular kind and the negative electrons which are sitting there, we have to ask a number of questions. For example, what holds the positive distribution charge together? Why does the charge all not fly away? That is an important question. And even if you do not address that question at this particular point, we would still have to answer what is it that maintains the equilibrium or the stability, because as I told you at least twice, it is impossible to have stability in an electrostatic situation. Even the least perturbation in any direction will disturb the atom, but the atoms are known to be there almost as long as the universe has been there. Atoms were synthesized very early. So, this is the apparatus which I spent a great deal of time with in order to explain to you what the experiment is. So, the important things that we have to remember is that the alpha particles, what we understand today to be helium nuclei, are coming with a large energy of 5.5 million electron volts. That is a very important piece of information for us. And this gold foil is a very thin foil which has very few layers of atom. It is not exactly very few layers, probably a few hundreds or thousands, but it is still very small compared to the bulk gold foil. And then even more importantly, you have this zinc sulfide detector which scintillates every time an alpha particle hits that, and then it is movable. I also told you in the last lecture that we should not take this picture completely literally. Of course, we know it is schematic, because this lead shield which is used for collimation is also rather overblown, because the detector could be moved very close to the beam direction, almost 180 degrees. Here it appears as if it is not possible, and that is what we find here. The results are illustrated in this figure, where you see that there are individual atoms, gold atoms, which are distributed over the foil. That is what you have, and the helium particles are all getting scattered. So what is happening to the alpha particle? You see, this is already a picture which is consistent with the planetary motion. So I will come back to that later. All that you have to notice here is that many of them are passing straight away, some of them are getting slightly bent, and some of them are getting very largely bent. There is almost a back scattering, there is a rebounding, like a ball goes and hits a wall and comes back. My alpha particle is hitting and its momentum is completely reversed. So this is something that we have to understand. So it is worthwhile remembering what we did in the last class, because this is very important data for us. What is the most important data? The energy of the alpha particle, the kinetic energy was 5.5 million electron volt, and as I told you, this energy is much larger than the mass of the electron or the rest energy of the electron. The electrons have typically something like electron volt energy in the atom. Anyway, even if you don't know that, the mass is something like 0.5 MeV by c squared. Alpha particles have 8,000 times the mass of the electron. I estimated that in the last lecture. So when I am looking at the interaction of the alpha particle here with the gold foil, it may interact with the electron, but then, as I told you, it is like a huge truck hitting a small pebble, because it is 8,000 times, almost 10,000 times heavier. The pebble may get scattered, but hardly anything happens to the truck which is moving with a certain velocity. That means the momentum of the alpha particle is practically unchanged because of the collisions with the electrons. The electrons may get knocked off, it does not really matter. The only care that we have to take in this detector is that this detector should respond only to the alpha particles and not to the electrons. That supposedly will be given by the intensity of the scintillation or whatever. Rutherford took care of it. That is something that you have to remember. That means whatever scattering is taking place, especially the large angle scattering, you should be predominantly because of the interaction between the positive charge in the atom and the positive charge carried by the alpha particle. Okay. This is another figure that I showed you in the last lecture. This is not Rutherford result. I will show you the Rutherford result in a while after describing the whole thing. Actually, it was an experiment performed by Geiger and Marsden. This is the scattering of proton, hydrogen ion, positive ion against gold, against phosphorus and against boron. The important point that we have to notice here is that there is a certain universality. All of them have qualitatively the same features. So you see, phosphorus has larger positive charge than boron. Gold has larger positive charge than phosphorus. Therefore, if you look at the cross section, which is essentially the number of alpha particles that are scattered as a function of angle, you see, it is maximum for gold, it decreases for phosphorus, and it is further smaller for boron. But otherwise, the shapes are roughly the same. You can scale them as if it can be translated. And the other important point is that the scattering peaks in the forward angle. That is where most of the scattering is. That is where most of the alpha particles are found. And as you keep on increasing the angle of scattering, you have 60 degrees, 80, 100, all the way up to 180. It is smaller, but the most important thing is that it is not zero. There is one more point that you have to notice in this figure. If you look at it very carefully, there is 0, 1, 2, 3 and there is a -1 written here, which I did not notice yesterday. Don't be put off. How can the number of scattered particles be negative? This graph is in the logarithmic scale. So you know, when a number is less than 1, the logarithm will become a negative quantity. That is what we have. That means when I go from 0 to 1, there is 1 order of magnitude jump in the scattering cross section. This is not a linear scale. So what you are actually plotting here is the log, that is what is shown here, log of the number of alpha particles that are seen. So this -1 should not put you off, because logarithm of a positive number can jolly well be a negative number. That is something that you have to remember. Okay, we summarize this. This is the experiment which I will come back to from the plume boarding, and this is the experiment of Geiger and Marsden. But before we do that, so let me stay in this particular figure. We have to do a certain bit of analysis. I started this analysis in the last lecture, but we ran out of time. Now I am going to complete it. I am not going to work out everything for you. I am going to leave a few things. Please work them out. Make your answers more accurate, more realistic. So let us start looking at these things. So the hypothesis that we make initially, which is exactly what Rutherford did, was to assume that the positive charge is distributed over the volume of the nucleus. So my nucleus, I can pick up another color, let us say red, has a radius r. So let us say my atom is a spherical object, and this has a radius r. So let us assume that my positive charge is distributed uniformly. We do not have to take it very, very seriously. In fact, it is all right even if you look at this scenario where my positive charge is probably contained in a certain region or volume in the nucleus, and it is perfect atom, and it is perfectly possible that the atom has this size. That also we can assume. What about the electrons? Maybe some electrons are here and maybe some electrons here. So the first one is strictly adhering to the Thomson model. Is that okay? Because all the positive charges, negative charges will be sitting inside. Here this is not exactly Thomson model, it is a partial Thomson model. We are saying some of the electrons are inside the positive charge distribution and some of the electrons are outside. So there are two limits. If all these get inside the positive charge distribution, then the red line becomes the size of the atom, that is Thomson model. Or if it so turns out that all the electrons are outside the positive charge, then we are negating the Thomson model, and in which case the location of the outermost electron will give me the size of the atom. We have to remember that. So I can put a outermost electron here, let us say, and this will be my radius r. So this is the picture that we are going to start with. What is happening now? What is happening now is that I ignore the negative charges, as I told you. So this is coming from the positive charges only, and here is an alpha particle almost at infinity. That is the statement that we are going to make, and at infinity it has a kinetic energy E is equal to 5.5 million electron volt. That is what we have, and this alpha particle is shot by the radioactive nucleus in this direction. Of course, the radioactive nucleus emits alpha particles in all the directions, but I have put two lead shields which essentially collimate, select those alpha particles which are coming in this particular direction, and then as it moves, it starts experiencing the field produced by this positive charge. So what is my nucleus? My nucleus is gold. Gold has 87 electrons. Therefore, the charge of the positive charge distribution, the total charge, is also equal to plus 87. It has an atomic mass which we should remember. A is of the order of is equal to 199, almost equal to 200. Just as my alpha particle is very, very heavy compared to the electron, you can see that my gold atom is also very, very heavy compared to the alpha particle. My alpha particle has A equal to 4, whereas gold has A equal to 200, so gold is 50 times heavier. It is not as dramatic as in the case of alpha particle and electron, but gold is 50 times heavier than an alpha particle atom. Therefore, again when you look at the scattering, you need not worry about the recoil of the gold atoms. So we are going to look upon the whole scattering as a scattering from a fixed target. These are the essential things that we have to know. That is what we have. Now let me look at the case where my alpha particle is arriving head on. What does head on mean? If I extrapolate, this will be the center. So in mechanics, we say this has zero impact parameter with respect to the center. That is what we are going to say. And therefore, with respect to the center, this has zero angular momentum. R cross P is equal to 0. Where otherwise, if it were somewhere here, there would have been an impact parameter, and impact parameter multiplied by the momentum would have given you the angular momentum. That is something that you have to remember. Now, at infinity, it had an energy of 5.5 MeV, but at any intermediate point, it will have kinetic energy plus potential energy. Kinetic energy plus potential energy. All of you know that in the field produced by the charges, the total energy is conserved. Therefore, total energy, which is equal to kinetic energy plus potential energy, is equal to 5.5 MeV. Always, wherever the charged particle may be. And this is valid not only if the collision is head on, my alpha particle can be coming here, it can be coming here, it can be coming here, whatever, it does not matter. Wherever it may be coming, it is going to be there. So you can see if it comes here, it is going to get scattered like this. If it comes here, it is going to get scattered like this, so on and so forth. But this total energy is a conserved quantity, and we are going to make use of that. Now, what is the question that we are going to ask? The question that we are going to ask is, how close to the atom can an alpha particle get? That is the question that we are going to ask, and that obviously depends on the size of the positive charge distribution. So I am going to make one estimate for you, and then I am going to modify that, which you will yourself work out. So let us do a crude analysis. What is the crude analysis that I can do? So imagine that all the positive charge is contained in a very, very tiny region, which is almost point like. So this is a underestimate of the closest distance, almost point distribution. That is what I have. Now in that case, how will the potential look like? The potential is of course repulsive. The force is repulsive. Therefore, the potential will look like this. Even the force will look like this. This is my 1 over r potential. So as you go far closer and closer to the target, so this is my target position, my potential energy keeps on increasing, and therefore, and as you go very close to the target, it almost becomes infinity. It is becoming very large. But then my total energy is a positive quantity, my kinetic energy is a positive quantity. Therefore, if a particle of a certain energy is coming here, depending on what its energy is, here it will come here, at this point all the kinetic energy will become 0, because my potential energy is equal to the kinetic energy at infinity, then it will get rebound. If I have a higher energy, it will come here, it will get rebound, so on and so forth. But in this picture, however large your energy may be, my alpha particle will never be able to reach the target, because this virtually goes to infinity. Now for the time being, let us ignore the finite size of the atom, and let us make an estimation of how close the alpha particle can get to, and then compare it with the size of the atom. So we are going to do it in 2 steps. The first step is ignore the size of the atom. Estimate, it is not actually an estimate, it is exact, but R minimum. This is the closest distance that the alpha particle can approach. Number 3, compare R minimum with capital R. This size is R. That is what we want to do. If this R minimum is greater than R, which is perfectly fine, we don't have to worry about it. But if R minimum is less than R, that is something that we have to worry, and let us look at that. The equations are very, very simple. The potential energy is simply given by Q1 Q2 over 4 pi epsilon naught R minimum is equal to the total energy at kinetic energy at infinity, which is the total energy, and that is nothing but 5.5 MeV. This is what we are going to equate. So let us remember, in the units of electron charge, Q1 is equal to 2, this is my alpha particle, and Q2, so alpha, gold is 87. This is something that we have to remember. That means Q1, Q2 is almost close to 100, 174, some such thing. Therefore, the force of repulsion is very, very large. Therefore, the potential energy is also a large positive quantity. 4 pi epsilon is the constant that we people are aware of. Therefore, what is my R minimum? R minimum is Q1, Q2 over 4 pi epsilon naught into 5.5 MeV. That was an oversight. This is what we have. If the charges become larger and larger, the minimum distance that you can approach becomes also larger and larger, because you cannot penetrate the barrier. That is what you are going to get, and this is a consistent expression. So let me repeat that calculation. Q1 Q2 over 4 pi epsilon naught R minimum is equal to 5.5 MeV. So I push R minimum here and I bring 5.5 here, and now everything is fine. So that is what we have. And of course, as the energy increases, R minimum decreases, because you are able to go through the potential barrier. So basically, it is a competition between the charges of the projectile and the target and the energy of the incoming projectile. This is the correct expression. I wrote a wrong expression, but we have corrected them. No harm so long as we correct. As I told you, Q1 and Q2 values we have already written. Let me repeat that here. Q1 is essentially of alpha, which is equal to 2 in the units of electron charge. Q2 equal to 87. What we can now do is to plug in the numbers. I will not plug in the numbers, I will leave that as an exercise for you. So if we plug in the numbers, what do we get? We get R minimum is of the order of 10 to the power of minus 14 meters. R minimum is of the order of 10 to the power of minus 14 meters. And what is the size of the atom? My size of the atom is of the order of 10 to the power of minus 10 meters. So we are saying that my alpha particle can penetrate very, very close to the center of the atom, making this assumption. Whether R minimum is an underestimation or an overestimation, that will come together. Therefore, R minimum over R is 10 to the power of minus 4. It is a very, very tiny fraction. That means you are almost hitting the center. Because this R minimum is 10 to the power of minus 14 meter, obviously my analysis is incorrect, because I assume that the potential is 1 over R everywhere. So now what I am going to do is to correct that scenario. So what we will do is to consider a uniform positive charge distribution, because that is the model that we are going to look at. This distance is R, that is what I have, and I am going to look at the potential as a function of R. That is what I am interested in. Now what happens? You people know from Gauss's law that so long as your projectile is outside this spherical charge distribution, my projectile or the test charge will look upon the field as a field produced by a point charge. That is what Gauss's law tells you. So, V of r is equal to, we are interested in the potential energy, Q1 Q2 4 pi epsilon naught r if r greater than or equal to r. That is what Gauss's law tells you. Now, once you come inside, there is a uniform charge density rho such that integral rho d cubed r is equal to Q2. That is what we are writing, which is equal to 87 in the units of electron charge, except that it is of the opposite sign. Again, you can use Gauss's law inside the sphere. So, if you use Gauss's law inside the sphere, everyone knows that the field rises linearly and therefore the potential will be quadratic. So, inside the sphere, field rises linearly, potential is quadratic in R. That is a very trivial exercise which you can all people R. That is what we have. What is the field at the center of the atom? The field is 0, because if you look at a spherical distribution of charge and if I put a test charge at the center, then it is pulled equally in all directions. Actually, because of the repulsion, actually it depends on the size of the charge, whatever, it does not matter, and therefore the net force acting on the test charge is equal to 0, whereas if it were a point charge, the force at the origin would have been equal to infinity. Now we see there is a great conflict between whether the charge is concentrated very close to the center or whether the charge is distributed uniformly over the sphere. That is the most important thing for us. So, let me draw the field for you and then let me draw the potential for you. So, this is my R, this is my electric field as a function of R. Okay, electric field is positive because it is produced by a positive charge distribution. So, what happens? Inside the spherical distribution, it starts raising linearly. So, this point corresponds to R and the outside it falls off like 1 over r squared. We should contrast this with what happens if the charge distribution is almost point-like. Then what would have happened? This line would have continued and it would have gone off to infinity. 1 over r squared everywhere, that is what would have happened. But now you see, this is the tipping point at the surface of the charge distribution. Now there is something very interesting that is going to happen to us, and that is very, very important for us. Let me write the energy diagram, and in order to do that, let me draw this figure once again. There is no harm in repeating that because it sort of allows us to settle our thoughts. So, I am going to draw a big picture here. So, I have one here and another thing, I will turn it for a minute, which is going to infinity. Okay, assume that this is going to infinity here. Now, let us look at what happens to the charged particle. Let us happens what happens to the alpha particle which is coming. So, this is my, so now this is my force. So, when my alpha particle is coming, if its energy is great enough, let us say more than this, so that it can reach a minimum distance more than this, then it can simply pass through. Not only will it pass through, as it gets more and more into this region, the magnitude of the electric field becomes smaller and smaller, therefore the repulsive force becomes smaller and smaller, therefore it is made further easier. That is the most important thing. So, a better way to depict this is actually in terms of the potential energy, because we want to show the energy diagram. So, what we have is potential energy V of r as a function of r. So, what is my potential energy? Can somebody tell me? Potential energy is very, very important here, because V is minus EdR. We should not forget that. Therefore, For r less than r, my potential energy becomes what? Negative. That is something that we have to remember. For r greater than r, of course it is a positive quantity. So the potential energy V of r is minus half kr squared for r less than r, and this is equal to q1 q2 over 4 pi epsilon naught 1 over r for r greater than r. Okay. We have to be a little bit careful here. This is not a very consistent way of writing things. Why is it not a consistent way? This expression q1 q2 over 4 pi epsilon naught 1 by r is written assuming that the potential is 0 at infinity, whereas minus half kr squared is written assuming that the potential energy is 0 at the equilibrium point, but you are allowed to choose 0 of the potential at only one particular point. Therefore, what I should do? I should write plus a constant. That is the most important thing. So this is a lesson that we learn here. So let me work it out. So we are saying that V of r is minus half kr squared plus a constant. This k you know, which comes from the force, I will fix that in a minute. That must be equal to q1 q2 over 4 pi epsilon naught 1 over r at r equal to r. This is something that you have to remember. So this constant is very, very important for us. Now how do I fix my k? I fix the value of k by simply equating the electric forces at r equal to r. So k is fixed by equating forces at r equal to r. So that is what we are going to do. That means we are going to write k capital R is equal to q1 q2 over 4 pi epsilon naught 1 over r squared by equating the forces. So what is my k going to be? My k is simply q1 q2 over 4 pi epsilon naught 1 over r cubed. So I will now write my potential to be V of r is equal to minus 1 over 8 q1 q2 over 4 pi epsilon naught into r squared by r cubed plus constant if r less than r, and this is equal to q1 q2 over 4 pi epsilon naught 1 over r if r greater than r. Now we can equate the potentials. The potential is continuous across the boundary. In fact, in this case the field is also continuous across the boundary, unlike the case of point charges or line charges, whatever. So we are going to equate. So what am I going to get? I am going to get 1 over 8 q1 q2 over 4 pi epsilon naught r squared by r cubed will be 1 over r plus constant is equal to q1 q2 over 4 pi epsilon naught into 1 over r. So the left hand side is coming from the sphere, inside the sphere, and this is outside the sphere. And at the boundary we match. Now my c can be easily fixed. So I am going to get a 1 over 8 plus 1 over 4, which is 3 by 8. So if I put a 8 here, I get to 3 by 8. Therefore my c is 3 by 8 q1 q2 over 4 pi epsilon naught into 1 over r. This is my constant. So, we have to do this much work in order to be able to write the picture of a potential. I am taking some care so that you people appreciate what is going to happening. Therefore, I can now write my V of r is nothing but I can pull the Q1 Q2 out, Q1 Q2 over 4 pi epsilon naught. So, let me write everything carefully. My C is 3 by 8, Q1 Q2 4 pi epsilon naught 1 over r minus, that is the most important for me, 1 by 8 Q1 Q2 over 4 pi epsilon naught r squared by r cubed. This is my expression for r less than r. And of course, r greater than r, it is simply Q1 Q2 over 4 pi epsilon naught into 1 over r. Please notice that dimensionally everything is correct, and probably we should at this point introduce a notation so that we do not keep on writing Q1 Q2 over 4 pi epsilon naught. So, let us introduce a constant big K at this and call it as Q1 Q2 over 4 pi epsilon naught. So, now if I am to equate the total energy, I have to make use of these expressions. So, since I already know that my alpha particle can penetrate inside the nucleus, I have to substitute in this particular expression. That I will leave it as an exercise for you, and you will find that it can go even much closer, and in fact at 5.5 MeV the alpha particles simply zoom through the nucleus. There should be no backscattering. That I will leave it as an exercise for you. So, what are we saying? I can now draw the potential. So, at r equal to 0, if you look at this expression, there is a 3 by 8, there is a 1 by 8, 3 by 8 minus 1 by 8 is 2 by 8, which is 1 by 4. It is a positive quantity. So, it is not starting with a negative quantity. So, my potential starts from a positive quantity. It decreases quadratically up to this particular point at r. That is what the potential is going to happen, and after that it will change slope and will go like 1 over r. This is r, this is quadratic decrease. And one can show your 5.5 MeV is something like this, and it can simply pass zoom through, therefore there should be no backscattering at all. Is that okay? Please remember, this is the picture of a potential. We have chosen the 0 of the potential to be at infinity, and my energy can simply go through, whereas the point particle picture would have given something like this. So, this is 10 to the power of minus 14, where it would have got repulsed, but now it simply passes through. So, it is said that when Rutherford asked this student Marsden to do this experiment, he did not expect any backscattering at all, because he worked this out and he said that there should be nothing interesting. So, this is the essence of Rutherford scattering. So, please work that out like I worked it out for 1 over r potential by equating the potential inside, and you will see that it can actually hit 0. There is no problem, very, very close to 0, and therefore, you should certainly not expect whatever the experimentalists find, for example, in this figure. So, in this logarithmic scale, if I look at very, very large angles, so let me show that for you. In the logarithmic scale, if I look at very, very large angles, the backscattering, if at all it occurs, should be so very small. The number of particles should be so very small. It is a very, very small number compared to 1. Therefore, in the logarithmic scale, this should go to minus infinity, because you know log 0 is minus infinity. When you are very, very close to 0, it should go to minus infinity, but there is a significant finite value. Now there is one more interesting that we have to worry about. If you have a uniform positive charge of this particular kind, and let us say the two alpha particles of the same energy are coming at the head on and at the periphery. Now whatever is coming near the periphery experiences a larger electric field compared to the one this, because it has already penetrated. That means the scattering angle for this must be larger than this, because this will simply pass through. Whereas if it is a point charge, the situation is different. Whatever is coming at the periphery of the atom barely gets scattered, because it is far away from the scattering center. But whatever is coming with zero angle, it is seeing an infinite force as it approaches the point particle, therefore there should be rebound. In other words, the plum pudding model predicts the particles which are coming at the periphery, all of them have the same energy, should get scattered more, but then the field is already small, therefore it cannot get scattered too much. The ones coming with zero impact parameter will not get scattered, they will simply pass through, because they have enough energy to pass through, because the electric field starts decreasing inside the medium. And this is just the opposite. And what does this experiment tell me? This experiment tells me that this picture is not supported. This picture is not supported. How is it not supported? And that is exactly what is shown in this cartoon. If you look at this, here is an alpha particle which has zero impact parameter with respect to the gold nucleus. It is getting rebound very badly. Whereas here is an alpha particle which is at the periphery of the atom, which sees very electric field, therefore it almost passes through. And here is another one which is not exactly head on but close to the central positive distribution, it is again getting scattered. This picture is wrong, because they have shown an attractive force instead of a repulsive force. Never mind about that. Is that okay? But this picture is correct, because the particle is coming very close, the repulsive force is very large, therefore it flies away. This unfortunately is a mistake on the part of whoever made it in Encyclopedia Britannica, but we completely understand this, and therefore we have to make a consistent picture, and this seems to be the consistent picture. Okay. Now there is another thing about the finite size distribution. This was qualitative. Quantitatively, what do we expect? If you work out the cross section, it is, you will learn it in your first year of your engineering or in your BSc. Whenever there is a size, the cross section falls as a function of scattering angle, but it does not fall monotonically, regularly. There is a periodic hump. It reaches a minima, then there is a hump, it comes down, it reaches a minima, there is a hump, it reaches a minima, there is a hump, so on and so forth. And do not be surprised too much by that, because in the case of de Broglie waves, you already saw that my de Broglie waves were conducted with electrons, right? The Davison-Germer experiment, it can exhibit a wave-like behavior. In a similar manner, even alpha particles can behave like as if they are wave-like, and they should show minima, maxima, minima, maxima, and this is what is going to happen. This is some kind of a vindication of whatever you see in the case, similarity with whatever you see in the case of Davison-Germer experiment. But this minima, maxima occurs if and only if the positive charge is distributed over a size. That is the condition. But what is it that the experimentalist found? This is the true experiment of Geiger and Marsden. Geiger and Marsden found, this is the Rutherford scattering experiment. See, this is the logarithmic scale, 10 to the power of 7, 10 to the power of 6, 10 to the power of 5, so on and so forth. You see, there are no humps, there are no minima, it is falling off regularly like this, okay? That is what we are finding, and from this we can conclude that the radius over which the positive charge is distributed is at least 10 to the power of minus 4 times the radius of the atom. This is a clinching experiment, because there is no evidence for the size of the positive charge distribution. And more importantly for you, you see there are two things here. One is the points and another is the curve. The curve is the theoretical curve which you get from the Rutherford formula, and the points are the experimental points, and you see that the experimental points are hugging the theoretical curve. There is absolutely no deviation That means that whatever hypothesis that we started with, that there is a, what do we call it, plum pudding model is ruled out, we have to assume that the volume over which the positive charge is distributed is very, very small compared to the volume of the atom. This is indeed the most crucial experiment for us. So once Rutherford got this experiment, he was mighty surprised and he immediately came up with an explanation. So he said that if atom has a certain radius r, which is 10 to the power of minus 10 meter, my positive charge is concentrated in a very small region which is less than 10 to the power of minus 14 meters. We are not asserting that the positive charge is a point charge. We are not asserting that. We are only asserting that my alpha particle does not have enough energy to probe lengths less than this. You have to send alpha particles of even higher energy, or for that matter it could be even electrons of higher energy. This kind of experiments were done by Hofstadter in 1960s. They are great experiments which reveal to us the structure of the nucleus itself. Now when you are encountering this particular situation, that means the electrons are all here and you look for a model and there is a God given, we mean Kepler Newton given model up in the sky, and that is the planetary model. Therefore Rutherford immediately postulated the planetary model for the atom. So he said that there is a central kernel or nucleus which is attracting all the electrons towards it, and the electrons, because of their own kinetic energy, they get trapped, but they do not fall into the positive charge, which is today we know is composed of proton and neutron, thanks to Chadwick and others, and it keeps going round and round, and this is your famous planetary model. So it should be aesthetically pleasing to everyone who wants to see a systematic pattern in nature. Therefore you say, if you are looking at length scales of the order of 10 to the power of 7, 10 to the power of 8 or 10 to the power of 10 meters, let us say, astronomical scales, and you are looking at a scale of 10 to the power of minus 10 meters, over these scales gravitation is there and they have the planetary model for the solar system, and in fact we know that there are binary stars which go around each other according to Newton's gravitational law. There are galaxies which are bound to each other by gravitational law. All that happens when we come from 10 to the power of 10 to 10 to the power of minus 10 is that the gravitational law gets replaced by the Coulomb law, but both of them are 1 over r potential, both of them are 1 over r squared potentials. So what we essentially have is the same thing reproduced at a smaller scale with a different interaction. So Rutherford should have been a happy man. But unfortunately, electrodynamics, electricity and magnetism are much more complicated than Newtonian gravity. So electricity and magnetism, the combined word is electromagnetism or electrodynamics. Much more complicated than Newtonian gravity. I used the word Newtonian gravity because we know that there is a more advanced theory of gravity which is called the general theory of relativity, and that is as complicated or even more complicated than electricity and magnetism. But for our purposes that is not important. Comparison with the Newtonian gravity is important, and let us see what it is. So if you look at this model now in this slide, this is the conventional picture that you have in your textbook. This is again from Britannica. So you have all the positive charge concentrated at the center, but then the positive charge does not account for the full mass. Therefore you have to postulate the existence of the neutral particles. Chadwick discovered them. So the blue ones are the neutrons, the grey ones are the protons. There are many more blue ones than the grey ones. Don't think neutrons are some passive objects which are sitting there. They have a very important role to keep the nucleus together. There is a big question of what keeps all the protons together when there should be a great repulsion. That is because at such short distances, the electromagnetic force is not the dominant force, but it is the nuclear force. We will learn that when we do nuclear physics after a few lectures, and there neutrons are very important because they also participate in the nuclear force. And now you have a picture where you show, so let us say 2 electrons in one orbit, 4 electrons in another orbit, so on and so forth. Don't take these numbers 2 and 4 very seriously, although they have some basis in the Bohr model. At this point you need not take. This is your planetary model. So all is well and good, just as you have planetary model for the solar system, which we realized after thousands of years of observation. Remember, astronomers have been looking up the sky and mapping the path of the planets and the stars over many, many years. But now, this is not as simple as that because there is a complication. So I want you to look at this picture. What we have on the left hand side is the energy in GeV of a proton in an accelerator. So let me describe you what that accelerator is. It is called a synchrotron. So let me write down the picture of a synchrotron. So basically in this synchrotron, what you have is protons moving in circular orbits because of a magnetic field. All of you know charged particles. But somewhere here, I am showing it very schematically, don't take it seriously. They will get accelerated and they will gain energy, and again they will go in a circular orbit and again they will gain energy. These accelerators are called synchrotrons. So this is like a planetary model for a proton, and you see in a synchrotron what is happening is that it is continuously emitting radiation. The energy that you are supplying, even if you don't supply energy, simply because of its acceleration it is continuously emitting radiation. I am sorry, this is the energy of the radiation that is coming, and this is the intensity of the radiation that is coming in a synchrotron. And in a synchrotron, proton can have as large as an energy as 30 MeV. In fact, it is there even in the cosmological scale. This is a radiation jet in space. Basically what I want to tell you is that all radiating charges, accelerating charges should necessarily radiate. So the big question is, how is the electron able to go around the proton without radiating? So posing this question, I will stop at this particular point. In the next lecture, we will investigate this feature even more. And there is another surprise called the spectral lines, and we will see how Bohr was able to get over both the problems with a stroke of a genius. So we will address that in the next class. Meanwhile, please solve the problem of the potential barrier. Goodbye.